Have you ever tried to hear the smallest conversation in nature? Not with ears, but with questions. Imagine a single atom, not exotic, just hydrogen switching energy levels and releasing a photon so precise it could set a clock. One step deeper, and electrons aren't dots anymore. They are allowed places, rules, and probabilities. Patterns appear, sharp lines in a spectrum, stable shells, bonds that hold matter together. From those quiet rules come stars, chemistry, and the light in your room. We'll trace how these whispers add up, how simple quantum limits scale into everything familiar. If clear, steady exploration is your pace, a light like and subscribe helps this reach others without breaking the flow. Take a breath. Let's follow an atom's voice from the lab bench to the night sky. Long before particle beams and cloud chambers, people tried to make sense of matter with clear eyes and simple tools. The questions were direct. What is everything made of? Can something turn into nothing? If you keep cutting a thing into smaller parts, do you reach a final piece that will not split? In the 5th century BCE, two thinkers from the Greek world, Leucippus and his student Democritus, offered a clean answer. There must be a smallest unit. They called it atomos, meaning uncuttable. It was not a metaphor. It was a claim about the physical world. All things are built from tiny, durable pieces that differ in size, shape, and how they move. They pictured atoms as solid and everlasting. Some would be smooth, some hooked, some heavy, some light. When these pieces collided or locked together, they formed the textures and substances we know. Hardness, they argued, came from tight packing and sharp shapes. Sweetness from smoother forms and looser arrangements. They added another idea many found uncomfortable: the void. A true emptiness where atoms could move. To many of their peers, empty space was either silly or dangerous. Nature, people said, does not allow a vacuum. But Democritus insisted that motion needs room. Without the void, atoms would have nowhere to go and nothing to do. He stretched the idea into the mind as well. He suggested that even the soul was made of very fine, very fast atoms, smooth and quick moving through the body. In that way, he tried to link perception and thought to the same physical rules that govern stones and streams. We would not use those details today, but the move itself matters. He tried to explain the world without calling on spirits or hidden essences. Atoms and void were enough. Other philosophers pushed back. Plato placed value on ideal forms, perfect patterns beyond the physical world. The things we handle and see, he argued, were imperfect copies of those higher shapes. A theory that reduces nature to motion and collision did not fit that view. Aristotle's influence reached farther still. He rejected the void and argued that nature is continuous. In his method, everything is made from 4 elements: earth, air, fire, water, guided by basic qualities: hot, cold, wet, dry. Materials change when these qualities shift. Fire warms and dries. Water cools and wets. The picture was elegant, connected to daily life, and easy to teach. It also tied neatly to ideas of purpose in nature. Every object, every motion, seeking its natural place. Over time, Aristotle's model pressed atomism to the margins. Scribes copied his works. Schools taught them. Debates hardened into tradition. Democritus's writings faded. Not a single complete text survives. What we know of his arguments comes from later summaries, some friendly and some hostile. Even so, his core idea kept a faint presence. The world might be built from small moving parts, and differences in matter might come from how those parts are arranged. If you have ever watched dust float in a shaft of sunlight and imagined tiny pieces always in motion, you have stood close to the picture he drew. There was a limit to how far talk alone could go. No lenses showed atoms, no scales measured their count, no careful tables of reactions existed. The atom was a useful guess, but still a guess. For nearly 2,000 years, attention turned elsewhere. People mixed practice with story, symbol with experiment, hope with heat. This was the age we now fold under the name alchemy. Alchemy took different shapes in different places, but a few threads run through them. It mixed hands-on work in a workshop with ideas about inner change. It promised that metals might transform lead to gold, and that the person at the furnace might be transformed as well. The roots ran across cultures: the Islamic world, medieval Europe, China, India. The ambitions reached from wealth to healing to long life. Tools improved because they had to. Glassware got better. Ovens grew more reliable. Distillation, crystallization, and evaporation became techniques with steps you could repeat. The language in alchemy was rich in signs. Without knowledge of atoms or molecules, people leaned on patterns and numbers. The four elements held their place, often joined by new principles to explain solidity, smoke, and flame. A metal might be described as a balance of hidden sulfur and mercury, not the common substances alone, but ideas of burning and fluidity within matter. It was not correct in the modern sense, yet it helped people look for structure. If materials change, maybe they do so because of internal parts that can be altered. In the 8th and 9th centuries, scholars working in Arabic pushed this system toward order. Jabir ibn Hayyan, often called Geber in later Latin texts, is tied to early recipes and methods that took laboratory work seriously. He catalogued how to purify and separate. He pushed for careful observation and clear steps. The theory that metals are mixtures of mercury and sulfur is tied to his circle. The theory is wrong, but the habit it encouraged, linking a substance's behavior to its inner makeup, was a step toward thinking that matter has a consistent structure. Across the centuries, European alchemists took up the same questions with local turns. Paracelsus, in the 16th century, brought medicine into the workshop. He argued that chemistry should serve healing. He added salt as a third principle, again symbolic, standing for stability and residue. This triad, sulfur, mercury, salt, did not map to atoms, but it urged people to see that burning, vapor, and solid leftovers point to distinct traits within a material. In practice, this focus shifted attention from gold making to remedies and processes. People recorded how acids bite, how bases soothe, how metals dissolve and reappear. In China, alchemy often aligned with Taoist goals like longevity. Workers handled cinnabar, mercury, and other compounds, watching how heat and time changed them. The aim might be an elixir, but the work still produced observations, colors shifting, crystals forming, fumes rising. In India, texts on minerals and medicine blended practical knowledge with philosophy. In each place, the mix of craft and thought kept the idea of transformation alive. Without a formal atomic theory, people still asked, what could change and why? The four-element picture held not because it matched every detail, but because it felt like a clean map. Fire dries wet wood, water softens dry grain, earth falls, air rises. You could tell stories about weather, growth, and illness using the same set of pieces. Doctors spoke of humors, fluids within the body seeking balance. Metal workers spoke of tempering and smoke. Farmers watched the sky, tilled the soil, and read the seasons in heat and damp. When a single framework reaches into many parts of life, it becomes hard to set aside. And because Aristotle denied the void, the stage had no place for tiny pieces flying through empty space. Still, the workshop kept nudging people toward structure. Labels and lists grew. Substances were named and sorted. Acids were grouped by what they could dissolve. Bases by how they neutralized sting. Salts by how they formed crystals from mixed liquids. Glass flasks let people watch a reaction instead of only its aftermath. Thermometers and balances brought numbers to the work. When you can weigh, you can compare. When you can heat by degrees, you can repeat. Slowly, a new kind of argument formed, not only from reason and tradition, but from measurement. What did not exist yet was a single picture to tie all the steps together. You could purify and react and write it down, but you could not say in simple terms what a substance is. The word element did not mean what it does today. It meant a basic quality or a simple ingredient, not a species of atom with a fixed number of protons. Even so, the idea that matter has types began to harden. Copper behaved like copper. Sulfur behaved like sulfur. Mixtures could come apart into pieces that looked and acted the same each time you found them. If the ancient atomists had returned to peek into these workshops, they would have seen little proof of their particles. Yet they would have recognized a habit that matched their own. Explain the world by regular behavior and consistent parts, not by mood or miracle. The difference is that the alchemists put their hands into the work. They boiled, measured, waited, and tried again. As the Middle Ages passed into the early modern period in Europe, the need for clear language grew. Merchants traded dyes, metals, and medicines. States wanted consistent coinage and reliable gunpowder. Glassmakers guarded recipes, yet had to deliver identical panes and lenses. You cannot meet these demands with symbol alone. You need repeatable steps, common measures, and shared names. The culture of craft pulled thinking toward standard practice. Arguments against the void still carried weight. Many thinkers felt that the idea of empty space broke the logic of motion. If there is nothing, how can anything move within it? Others tied their doubts to theology or natural philosophy. A continuous medium was easier to picture. Yet in physics and astronomy, new cracks opened. The study of falling bodies and moving planets hinted that rules could be simple and universal. If laws were uniform, perhaps matter was uniform at some deeper level too. In the background, small tools pushed forward. Better furnaces allowed controlled heat over long periods. Improved glass reduced contamination and revealed color changes that once went unseen. Balances grew sensitive enough to show that the sum of masses before and after a reaction stayed the same within the limits of the day. Once you notice that, you start to suspect that there are units being conserved, even if you cannot see them. It helps to pause and look at what alchemy did get right in spirit. It treated matter as transformable, not fixed by status. It taught that processes grinding, heating, dissolving, precipitating can change how a substance looks and behaves. It demanded attention to detail and time. It built a laboratory culture of notes, controls, and comparisons. These habits carried into chemistry. When modern chemistry emerged, it kept the bench, the jar, the flame, and the logbook, but swapped symbols and essences for counting and atoms. The influence of place matters too. In the Islamic Golden Age, scholars preserved and critiqued Greek texts, adding their own methods. In Europe, contact with those works through translation fed universities and guilds. In China and India, local traditions gave different paths to similar observations. When you heat a mineral and collect a colored smoke, it does not matter which story you tell about it, the observation can be stored and shared. Over time, shared observations pull people toward shared explanations. The atomic idea had not been proved, only shelved. It waited for a culture that would accept invisible entities if they made testable predictions. That culture needed instruments, methods, and a taste for numbers. It needed the sense that a good explanation should work in many places, not only where it was born. It needed the patience to let experiments decide between pictures that felt elegant and pictures that matched the measurements. There is a simple lesson in this long, quiet stretch. Ideas can be early. A clear guess may arrive centuries before tools can test it. That does not make the guess useless. It gives direction. It sets a target for later work. Atomism set a target. Find a way to show that matter comes in discrete units that move in empty space. Alchemy, in its many forms, kept the workshop alive long enough for that search to become practical. When people finally returned to the atomic idea with fresh tools, they did so with a bench full of techniques. They could separate and combine with purpose. They could weigh before and after. They could seal a vessel and watch gas form. They could heat to a known temperature and hold it steady. They could write a recipe that another person could follow in another town and expect the same outcome. Those abilities turned whispers into tests. Even the resistance to the void played a role. By arguing against empty space, thinkers sharpened their definitions. What counts as motion? What counts as a medium? How do you measure pressure or resistance? Those questions lead to pumps, barometers, and the study of gases. When you pump air from a chamber and a flame goes out, you learn that something in air supports burning. When you let air back in and the flame returns, you find that the chamber had been close to empty. Step by step, the void becomes less scary and more measurable. If we line up the story so far, the sequence is calm and clear. First, a bold claim, smallest parts and empty space. Next, a long period where practice grows, but the claim sleeps. Then, craft reaches a level where counting and control become normal. The stage is set for a return to discrete units. Only now, the units can be tied to weights, volumes, and fixed ratios. The language shifts from symbol to number. The furnace keeps burning, but the notes become tables. Craftspeople and scholars in workshops and libraries weren't trying to hand a baton from Democritus to modern physics. They chased local goals: a brighter dye, a safer remedy, clearer glass. Yet their careful notes, recipes, weights, colors, failures built a record others could test. So when atom-based ideas returned, they didn't float on philosophy alone. They stood on measurements made by steady hands that heated, stirred, sealed, and watched. That foundation matters. Today we can check claims about atoms with tools. Spectral lines that reveal electrons stepping between fixed energies. Gas laws that show elements combining in constant ratios. Microscopes that send surfaces atom by atom. But the road to such certainty ran through centuries when certainty wasn't possible. People still refined vessels, named substances, and wrote down what they saw. By the 1600s, that habit of testing began to press hard on the old quartet air, fire, water, earth. Across Europe, investigators heated, weighed, and sealed materials to learn what they were made of. One puzzle rose above the rest: air. It was invisible and seemed weightless, yet it filled every space and kept flames and lungs alive. Was it a kind of nothing, or a material with structure that could be measured? Robert Boyle treated air as a substance that could be studied. He was careful, patient, and willing to test claims that others took for granted. With the help of Robert Hooke, he built strong glass vessels and an improved air pump. This pump could remove most of the air from a container and let him watch what changed. When he pumped air out, a candle went out faster than usual. A bird or mouse could not breathe and soon weakened. Sound faded. These simple results showed that air was not nothing. Air had properties that supported fire, sound, and life. Boyle and Hooke also learned that air could be squeezed and that this squeezing had a clear effect. When a fixed amount of air was forced into a smaller space, the pressure rose. When the same air was given more space, the pressure fell. Boyle wrote the relation in a clean rule that we still teach. At a steady temperature, the pressure of a gas is inversely proportional to its volume. Half the volume, double the pressure. Double the volume, half the pressure. This was not a story or a symbol. It was a measured pattern that anyone could repeat with the right tools. The air pump did more than create nothing. It created conditions to test ideas. Aristotle had said nature does not allow a vacuum. Boyle did not answer with debate. He answered with a jar. Inside that jar, flames died and lungs failed because the useful part of air had been taken away. In this way, he pulled science toward experiments that decide between pictures of the world. Hooke was far more than a helper. He refined the pump, designed experiments, and pushed the work into new areas. He looked through microscopes and drew what he saw. He studied springs, light, and building design. In the study of air, he tested how living things change when air is removed or changed. He suggested that something in air is used up in burning and breathing. The something would later be named oxygen by others. But Hooke's point was already strong. Air is a mixture with parts that do different jobs. The idea that gases act like many small moving particles began to feel useful. If tiny bits bounce off each other and off the walls of a container, then pressure is the push of those bounces. Temperature links to how fast the bits move. Changes in volume change how often and how hard those bits strike the walls. Democritus would have recognized the spirit of this view. The difference now was method. The picture was not just a guess. It was backed by pumps, gauges, and numbers. Boyle also worked to clean up language. In his book, The Sceptical Chymist, he questioned the old scheme of elements and qualities. He argued that substances are made of small corpuscles that combine in different ways. Corpuscle here meant a tiny piece of matter, not yet an atom with a fixed identity, but still a step away from vague essences. The book asked for tests, clear terms, and measured claims. It pushed against tradition without insults. It asked readers to trust careful results over old names. A simple but important point followed from this approach. Air has weight. Many people thought that if you cannot see something and it seems to float, then it must be weightless. Boyle showed otherwise by trapping air in a sealed vessel and placing it on a balance. The scale changed when more air was added or removed. Weight could be counted. From there, the study of gases opened. Later, workers would isolate hydrogen, oxygen, and nitrogen. But in this period, the key gain was more basic. Air is a kind of matter. It can be compressed, expanded, weighed, and studied like any other material. As this style of work spread, chemistry began to look less like coded recipes and more like measured steps. Barometers and thermometers made pressure and temperature into numbers. Air pumps and sealed flasks made controlled spaces. Scales turned more and less into grams. That shift mattered. It made it possible to compare results across time and place. A lab in one city could repeat a process done in another. Agreement became a goal. In France, a careful worker took that goal as his calling. Antoine Lavoisier focused on weighing everything that went into and came out of a reaction. He did not hunt for gold or elixirs. He did not chase atoms he could not yet prove. He asked a clear question. When a material changes, where does the mass go? At that time, many people believed in a theory called phlogiston to explain burning. The idea said that combustible things contain a special stuff, and when they burn, they release that stuff into the air. If a metal was heated and turned into a powder, the story went, phlogiston had left. The trouble was weight. Some metals got heavier when they were heated in air. To save the theory, some said that phlogiston might have negative weight. Lavoisier did not accept that. He chose to measure each part of the process and remove the guesswork. He built a well-equipped laboratory with sealed glassware, precision balances, and systems to collect and measure gases. He used closed vessels so that nothing could escape without being counted. He heated metals like mercury in a fixed amount of air and watched both the metal and the air change. The metal formed a red powder, now called an oxide. The air in the vessel lost some of its volume. When he heated the red powder by itself, a gas came off and the shiny metal returned. Step by step, the parts added up. A portion of the air had combined with the metal and could be released again. From these and other trials, Lavoisier reached a simple rule. In a chemical reaction, mass is conserved. Matter is not made from nothing and does not vanish. It changes partners. It moves from one form to another. If you could collect the gases, solids, and liquids involved, their total mass before and after would match. This rule is now called the law of conservation of mass. It sounds obvious to us because we learn it early, but at the time, it cut through centuries of loose talk about essences and spirits. Lavoisier's focus on measurement changed more than one theory. It shifted the whole field. Instead of saying a mixture smelled sweet or turned blue, he asked, how much gas formed? How much heat was released? How much mass changed hands? He helped give chemistry a new language with names that meant specific things. He pressed for a list of true elements, substances that could not be broken down further by known methods. He helped fix the names hydrogen and nitrogen and used oxygen for the active part of air that supports burning. He guessed that oxygen was in all acids, which later turned out not to be true, but the mistake did not weaken his main work. What mattered was the process. Observe, measure, repeat. His book Traité élémentaire de chimie became a guide for students and workers. It set out reactions using equations. It offered a system for naming substances that matched their behavior. The goal was clarity. With shared names and rules, people could talk about the same things without confusion. The old earth, air, fire, water, said faded from use because it did not match what the scales and flasks were showing. Lavoisier's lab had help. His wife, Marianne, translated papers, drew apparatus and results, and edited texts. Drawings made the setups clear. Translations linked French work to English reports and back again. The lab became a place where others could see exactly how to repeat a test. Clean diagrams, sealed vessels, and careful balances replaced riddles and symbols. The story around him was not calm. As the French Revolution grew, Lavoisier's role in tax collection made him a target. He was arrested and executed in 1794. The loss was deep, yet the methods he used did not vanish with him. They were copied and taught. The idea that reactions should balance, that gases should be measured, that names should be standard, kept growing. A clearer picture of combustion followed. Burning was not a release of phlogiston. It was a reaction with a part of air oxygen. Rusting, too, was a slow form of the same process. Metals gained mass because oxygen joined them. When something calcined, it formed an oxide. When the oxide was reduced, oxygen left and the metal returned. The parts could be weighed and counted. The numbers matched from one lab to another. This style of thinking led to more careful lists of substances. Some materials were elements, others were compounds, made from elements in fixed ratios. If those ratios were fixed, then there must be some regular units combining in set counts. The path toward atoms as counted units began to make sense, not as a guess, but as a way to explain why numbers came out so neat. If water always breaks into the same parts by mass, then its pieces must not be random. None of this required talk of electrons or nuclei yet. It required balances, sealed flasks, heat, and patient notes. The precision of the balance made ideas sharper. If a sample gained 2 grams when heated in a closed vessel, then 2 grams had come from the air. If the vessel lost 2 grams of gas, then the account closed. The habit of closing the account of matching inputs and outputs gave chemistry a solid floor. Boyle and Hooke had opened the door by treating air as matter that could be measured and controlled. Lavoisier walked through by showing that all chemical change obeys conservation. He tied flames, rust, breath, and acid formation to specific parts of air and to fixed changes in mass. He rebuilt the language so that others could share and test the same claims. He replaced vague principles with elements you could list and weigh. With that, the study of matter became less about hidden qualities and more about patterns you could verify. A gas was not a ghost. It had weight and took up space in ways that followed rules. A reaction was not a mood. It was an exchange that could be counted. A name was not a symbol hinting at a story. It was a label with a definition that matched a test. The work did not answer every question about structure. It did not describe atoms as we do now, but it made a safe path toward them. If matter is made of parts, then those parts must show up in the numbers. If gases follow steady relations between pressure, volume, and temperature, then something regular lies underneath. If compounds form in fixed ratios, then there must be basic units combining in set counts. These are quiet steps, but strong ones, and they rest on the same tools: sealed glass, steady heat, a sharp eye, and a reliable scale. By the end of this period, the field had changed shape. People could isolate gases, name elements, and write balanced equations. They could test claims about burning, breathing, and rusting with controlled setups. They could compare results from different labs because the tools and terms were common. The strange mix of art and symbol that had guided earlier work gave way to a method that prized repeatability. The change in mood was not theatrical. It was practical. A flame in a closed vessel used up a part of air. A metal heated in air gained mass by taking up oxygen. A gas compressed to half its volume pushed twice as hard. Each claim could be shown, not just said. In that setting, the idea that matter has structure could grow without guesswork. It could grow from the ground of numbers. Under this method, nature didn't hinge on hidden essences, but on measured change. If a substance reacted, every gram was counted. If a gas expanded, its push on the walls was recorded. Names matched tests that anyone could repeat. Piece by piece, matter became a cleaner picture, less guesswork, more numbers. Progress moved towards smaller parts, not by dream, but by count. The world wasn't magic. It was math in motion. In workshops that smelled of oil and warm glass, that habit of measuring turned into routine. Air was weighed, gases were trapped, reactions were balanced. On this footing, a quiet teacher from northern England made an old idea practical. John Dalton grew up counting rain and writing down pressure. He logged clouds the way others kept ledgers. Those patient notes, steady units. No fuss followed him into chemistry. Where many saw a blur of properties, he looked for parts you could count. Dalton asked a plain question. If substances always combine in steady proportions, what are we really measuring? When water is made from hydrogen and oxygen, the parts enter in fixed amounts. When carbon and oxygen form carbon monoxide in one case and carbon dioxide in another, the amounts rise by a simple step. These clean ratios did not look like luck. They looked like arithmetic. Dalton treated that arithmetic as a sign of structure. He set out the view in simple terms. Matter is made of atoms, tiny units that do not break in chemical changes. Atoms of one element are all alike in mass and in how they behave. Atoms of different elements have different masses and properties. Compounds form when atoms of different elements join in whole number counts. Chemical reactions move atoms around. They do not create or destroy them. This picture matched the scales and flames that chemists used every day. It did not ask for hidden fluids or special essences. It asked to track pieces that behave consistently. To keep ideas clear, Dalton drew atoms as circles with marks. A plain circle might stand for hydrogen. A circle with a dot might stand for oxygen. A circle with a cross might stand for iron. The drawings were not the atoms themselves. They were a map for the bench. They let a chemist show on paper that 2 hydrogen units and 1 oxygen unit make what we call water. They let a chemist show that 1 carbon unit and 2 oxygen units make carbon dioxide. The drawings gave a steady language for talk and for tables. Dalton linked those marks to mass. He adopted the term atomic weight to mean the relative mass of one kind of atom compared with another. He took hydrogen as a base unit, set it to 1, and tried to find the relative masses of other atoms by how they combined. It was not perfect. He did not always know the true formulas, so early weights had errors, but the move was powerful. If a compound forms in a fixed mass ratio, and if atoms are counted in whole numbers, you can work backward to find relative weights. A wrong formula gives a wrong number, but the method itself holds. This approach explained patterns that had bothered chemists. It explained why the same elements join in more than one way, but only in simple steps. Carbon and oxygen can pair as CO or as CO2. Dalton's model called this the law of multiple proportions. when one element combines with a fixed mass of another to form different compounds. The masses of the first element that combine are in simple whole number ratios. Those small integers signal countable pieces. The model also fit the law of definite proportions, already seen in careful work. A given compound always contains the same elements in the same fixed mass ratio. Whether water is made in Paris or Manchester, collected from rain or from a flame, the hydrogen to oxygen ratio by mass is the same. Atoms joining in fixed counts make that rule natural rather than a surprise. Dalton's tone stayed modest. He did not claim to see atoms. He claimed that if atoms exist, they explain the numbers. That stance matched the documentary spirit of his notebooks. He used the fewest assumptions, kept to whole number counts, and returned to the bench to check sums. He accepted that the details might change as formulas improved, but he thought the core would stand, parts that do not split under chemical change, joining in integer counts to make everything we handle. His life kept the same shape as his method, plain, steady, and dense with records. He taught, walked, and wrote. He kept daily weather logs for years. He studied color vision and described a condition later called color blindness. In chemistry, he took what the balance and measure had made possible and gave it a framework. He did not ask for praise. He asked that the arithmetic of reactions be taken seriously. Others took up the work. They refined atomic weights by correcting formulas and improving purity. They separated gases with more care. They compared results across labs and adopted shared symbols. The idea that elements have fixed identities gained strength. If chlorine always enters reactions with the same relative mass and makes predictable compounds, then an identity sits behind the name. As more elements were identified and measured, chemists began to notice families. Some elements reacted with water in related ways and formed salts with similar shapes. Others pulled electrons from partners with similar strengths, though that specific language would come later. In the early view, people spoke of valence, how many units an atom tends to use when it joins, and they used that to sort and predict. Those patterns tempted a higher order, a map where elements took places based on repeating traits. Across Europe, lists thickened. In each list, someone saw a rhythm and tried to write it down. Some started with atomic weight, since that was the main number every element carried. Others started with how an element behaved, what it did in acids and bases, what kinds of oxides and salts it formed, how many parts it tended to combine with. Attempts to align those two, weight and behavior, tugged in different directions. The best arrangement would need to respect both. In Russia, Dmitry Mendeleev set the problem on a table, literally. He wrote each element on a card: name, atomic weight as then known, common compounds, density, and typical valence. He spread the cards and moved them by hand, looking for an order that did not break when new elements were added. He sought a sequence that let similar elements line up in columns while weights climbed along rows. He allowed himself to move a card if the weight seemed wrong, because the behavior the family traits had to hold. The layout that emerged showed a periodic return of traits. Place the elements in order of rising atomic weight, and properties recur at intervals. Soft, highly reactive metals like lithium, sodium, and potassium share a column. The halogens, fluorine, chlorine, bromine, iodine, share a column, each eager to form salts with metals. Metals with several oxidation states line up across the middle. The order was not only pleasing, It was useful. It told where to expect certain types of compounds and where to look for relationships in reactivity. Mendeleev did not force every case to fit the then-known weights. In the pair of tellurium and iodine, the measured weights suggested one order, but their chemical behavior suggested another. He chose behavior. He placed iodine after tellurium in the column with chlorine and bromine, where its reactions made sense. He trusted the pattern of properties more than the printed numbers, and in time later, measurements and new concepts would justify that choice. The strongest test of his table came from the gaps he left on purpose. Where the pattern called for an element but none was known, he kept the space open and wrote down what should fill it. He listed expected atomic weight ranges, densities, oxide formulas, and typical compounds. He gave the predicted elements temporary names with the prefix Eka, meaning one beyond. Eka aluminum would later be found and named gallium. Its density, melting point, and oxide matched his notes within small margins. Eka silicon became germanium, with properties close to those he had written. Each success made the table feel less like an index and more like a structure. The method that led to the table was simple and firm. Gather reliable data, sort by one clear measure, and check against behavior. The cards were not tricks. They were a way to see many facts at once. The columns were not theories in the abstract. They were families with shared habits. When the families held as new elements were discovered, confidence grew. Skeptics softened as predictions landed. Teachers adopted the table for students to learn not just lists, but relationships. The periodic table also offered a calm response to the confusion of names and local customs. With a grid, an element had a defined place and neighbors that made sense. If two elements shared a column, a chemist could expect similar forms of oxides and chlorides. If an element sat in a row between others with certain densities and melting points, a rough value could be guessed before measurement. The map saved time at the bench and added order to books and shelves. Mendeleev worked without knowledge of protons, electrons, or the modern idea of atomic number. The charge inside the nucleus that we now use to define place on the table was not yet known. Radioactivity had not been mapped. Isotopes, atoms of the same element with different masses, had not been described. Even so, the periodic repeat of properties was strong enough to correct errors and to guide search. Where the pattern broke, people checked the weights again. Where a column seemed to lean, they looked for a missing card. The story of his life often gets told with color, distance, hardship, a long road to study, but the important part for the bench is the work itself. Careful notes, patience with messy data, and a willingness to let the pattern speak. He taught, wrote, and refined. He argued for standards in industry and science. He treated chemistry as a field that could be made consistent across places and languages if the core facts were sorted in a way that matched nature. As the table spread, it shaped how chemists thought about reactions. Valence patterns made predictions about what compounds could form and in what ratios. Columns suggested what could replace what in a salt or an acid. Rows suggested gradual changes in properties as one moved from metal to non-metal. The grid did not solve every detail, but it offered a strong frame for questions and a place to put answers where others could find them. The gains of the century, pressure and volume laws for gases, conservation of mass in reactions, atomic weights linked to fixed ratios, and a table that organizes elements by repeating properties formed a connected set. Each part supported the others. A reaction that obeyed conservation could be written with counted units. Counted units fit into a table where families repeat. Families predict compounds and guide searches. The daily work at the bench, heating, weighing, dissolving, filtering, fed the larger map, and the map fed back into the bench. Dalton's dots, tied to weights and ratios, made atoms practical to think with. Mendeleev's grid, tied to families and gaps, made elements practical to search for and name. The two efforts shared a style. Start with clear facts, arrange them with simple rules, and hold the results steady enough that others can test it. Neither required grand claims about what atoms look like inside. Both were strong because they matched what glass, flame, and scale could show. When new measurements revised atomic weights or corrected formulas, the framework didn't break. The table flexed to fit better numbers. The atomic picture absorbed isotopes without losing identity. Corrections weren't threats, they were steps toward clarity. That steady attitude kept chemistry from drifting back to symbols and stories that failed the bench. What began as a teacher's way to explain fixed ratios with countable parts became a common language. Index cards on a desk turned into a map on every lab wall. The moves stayed the same. Measure, compare, sort, predict, check, and write it down so others can repeat it. That map grew sharper once scientists learned what truly orders the elements. Placement is not set by atomic weight, but by atomic number, the positive charge in the nucleus, the count of protons that defines each element. Careful X-ray studies in the early 1900s showed each element has a distinct spectral pattern tied to its nuclear charge. With that link, the few mismatches in weight-based lists vanished. Tellurium and iodine sit where they do because iodine has one more proton, not because of a small mass difference. Mendeleev couldn't have known atomic number, yet by grouping elements with shared behavior, he put most of them in the right places anyway. Mendeleev was not only a classroom chemist. He worked on practical problems that required the same steady judgment. He advised on oil refining, argued for standards in industry, and studied agriculture. He even pressed for consistent measures in everyday goods. The traits were the same as in his table: sort what matters, define units, and compare fairly. His career shows the same habit of mind across fields: measure, classify, and expect patterns that can be checked. The table that grew from those habits is now part of basic education. New elements have been added as laboratories create or detect them. Rows have been extended. Names and symbols have been standardized across languages. The structure still stands because its backbone, ordering by atomic number and grouping by recurring properties, continues to match what experiments show. Students use it to predict likely compounds. Engineers use it to choose materials. Astronomers use it to interpret the light from stars. It works as a reference and as a tool because it encodes both identity and behavior. As industry expanded and instruments improved in the late 1800s, atoms were treated as the final units of matter. Dalton had given them identity and mass. Mendeleev had arranged them in a pattern that predicted new members. Most researchers pictured atoms as solid, featureless spheres that join and separate according to simple rules. That picture was about to change under glass in quiet laboratories that studied electricity in gases at low pressure. Vacuum tubes made it possible to pull most of the air from a sealed glass cylinder and to place two metal electrodes inside. When a high voltage was applied, a narrow glow formed, starting at the negative electrode, the cathode, and extending across the tube. The glow produced sharp shadows, made certain paints fluoresce, and could push tiny paddles. These effects showed that something leaving the cathode traveled in straight paths and carried momentum. Some called the beam a new kind of light. Others suspected particles. The tools were ready to decide. J. Thomson and his team at Cambridge built a tube that let them apply electric and magnetic fields to the beam. If the beam contained charged particles, the fields should bend it. By measuring the deflection and knowing the fields, they could calculate the ratio of electric charge to mass for the beam's carriers. The result was unlike anything known for atoms. The charge-to-mass ratio was far larger, which meant the mass was far smaller. The carriers were roughly 2,000 times lighter than a hydrogen atom. They were not atoms at all. They were parts from within atoms. Thomson called these carriers corpuscles. The term electron became standard soon after. The conclusion was direct. Atoms contain tiny negatively charged particles that can be pulled out in the tube. If atoms have negative parts, yet are neutral overall, there must be positive charge as well. Atoms were no longer indivisible in the chemical sense. They had internal components. Chemistry's stable counts could still hold, but the image of a solid ball had to give way to a structure that included charge. To picture how charge is arranged, Thomson proposed a simple model. He imagined each atom as a diffuse sphere of positive charge with the lighter negative electrons embedded within it. The total positive charge equaled the sum of the negatives, so the atom as a whole had no net charge. This pudding picture was not meant as an endpoint. It was a placeholder that matched the key facts. Electrons exist, atoms are neutral, and something positive is present to balance them. The model fit some observations. It allowed currents in metals to be thought of as electrons moving under an applied field. It explained how the beam in the tube could be deflected and why charge could be added or removed from objects in small, regular steps. But the model also had limits. It did not give a clear reason for the sharp lines of color seen when elements are heated in a flame or excited in a discharge. It did not show how electrons were held in place without radiating energy continuously. It solved the immediate bookkeeping of charge, but left questions about structure and light. The next step came from a series of measurements that used a new probe. Fast, heavy particles given off by certain radioactive sources. Ernest Rutherford, who had already sorted radioactive emissions into alpha, beta, and gamma by how they penetrate matter, directed a beam of alpha particles at a very thin sheet of metal, often gold. Alpha particles carry a positive charge and have significant mass compared with electrons. The setup surrounded the foil with a detector screen that flashed when an alpha particle struck it. If the atom were a diffuse positive cloud, the beam should pass with only small deviations. Most alpha particles did pass through with little change, which fit a picture where most of an atom offers little resistance, but a small fraction deviated by large angles and a few bounced nearly straight back. To rebound, a particle had to get very close to something massive and strongly positive. That something had to be far smaller than the size of an atom, otherwise the beam would have been scattered more often. Only a compact center, with most of the atom's mass and all of its positive charge, could account for the data. Rutherford proposed the nuclear atom. In this view, almost all of an atom's mass and all of its positive charge are concentrated in a tiny nucleus. The electrons carry negative charge outside that center. The space between nucleus and electrons is vast on the atomic scale. If the nucleus were the size of a small bead, the region where the electron is usually found would be on the scale of a large room or a field. This picture explained the strong, rare deflections. Most alpha particles pass through empty space. The few that aim near the nucleus feel a sharp repulsive force and turn aside or reverse. With the nuclear model, basic counts gained clear meaning. Atomic number became the number of protons in the nucleus. That number sets the positive charge and determines the element's chemical identity. Electrons match that charge in number for a neutral atom. The mass of an atom is dominated by the nucleus. Differences in mass between atoms of the same element, later called isotopes, could be understood as differences in nuclear makeup rather than changes in identity. The nuclear picture also reopened questions about motion and light. If electrons move around a nucleus, what paths do they take? A charged particle that curves should radiate energy according to classical rules. If electrons lost energy steadily, they would spiral inward, which does not happen. At the same time, heated gases produced sharp spectral lines, exact colors unique to each element, which suggested that electrons change energy in fixed steps. A stable atom with sharp lines called for a model where electrons occupy allowed states. That work followed soon after, but it did not erase what Rutherford had shown. The atom has a dense, positive core and light, negative parts that do not fill the space uniformly. Thomson's role did not end with the electron. He and his students developed techniques that separated charged particles by their charge-to-mass ratio. Those methods became the basis for mass spectrometry, which allows precise measurements of isotopes and molecular fragments. He studied ions in gases and showed that charge comes in small, constant units, consistent with a basic quantum of electricity. He trained students who would make major advances, including the one who redesigned the atom around the nucleus. Rutherford's lab continued to map the nucleus itself. By studying how particles scatter, his group inferred sizes and charges. They identified the proton as a charged nuclear particle, and later work would add the neutron. Each step kept the same approach. Use a known probe, measure angles and energies, and infer structure from patterns that repeat. The scale was new. The logic stayed familiar. The new atom changed practical work as well. Chemical bonds could be related to how outer electrons are arranged. Periodic trends made sense as patterns of electron count and shell filling, rather than only as similarities in behavior. X-ray methods, tied to electron transitions near the nucleus, let researchers identify elements in mixtures and in distant stars. The old table gained a deeper anchor in the count of protons. The weights on the table became sums of nuclear parts plus a small share from electrons. A thin sheet of metal, a sealed source, and a dark screen were enough to redraw matter. In the gold foil test, alpha particles struck the foil and made tiny flashes on a coated screen. Most went straight through, a few veered off, and a rare few bounced back. The setup was simple. The pattern was decisive. You didn't need giant machines, only clean materials, careful angles, and patience to count. From those counts came a new atom. The old indivisible sphere gave way to a structured system with measurable parts, a compact, positively charged nucleus that carries almost all the mass and sets identity, and electrons outside it that set size and chemistry. This model explains sharp spectra, chemical bonds, and radioactivity. The atom is not a solid lump. It is a dense core with moving charge, defined by numbers that instruments can detect and tables can list. Rutherford ran his lab with clear rules. Keep the apparatus honest, keep the thinking simple, follow the numbers. He liked direct tests more than fancy talk. When students stalled, he pushed them to restate the question and find the quantity that could actually be measured. That approach turned surprise into information. In this case, The surprise was the rare but large deflections. For a charged particle to bounce back, it had to meet a strong positive force in a very small region. A spread-out smear of charge could not do that. The only explanation that fit was a compact, heavy center, a nucleus surrounded by much empty space. The picture that followed was plain and strong. Almost all an atom's mass sits in the nucleus. The nucleus is positively charged. Electrons carry negative charge outside that center. The space between is not packed with matter. It is mostly empty at the scale of the atom. This was a hard shift for anyone used to thinking of atoms as solid balls, but the data left little room for the old view. You could keep the old words if you liked, but the angles on the screen said otherwise. Rutherford did not stop at structure. He and his co-workers studied radioactivity and nuclear change. They showed that one element can turn into another by events in the nucleus. That insight moved the idea of element from a fixed label to a state that could shift under the right conditions. Later, by firing particles into nitrogen, Rutherford saw a reaction that threw out a hydrogen nucleus. He had broken apart a nucleus and found a smaller charged piece inside. The path toward nuclear reactions was open, and with it, the study of energy tied to the nucleus. The gold foil test also changed how people thought about solid matter. If atoms are mostly empty space, then why do objects feel hard? The answer sits with electric forces. Electrons in one atom repel electrons in another when they are pushed close. Nuclei never come near each other in normal conditions. What we call solid is a stable arrangement of charges at small distances, not a tight packing of tiny marbles. The everyday feel of a table comes from forces, not from solid blocks pressed without gaps. The nuclear model left open many questions. What holds the positive core together if like charges repel? Why are some nuclei stable while others fall apart? How do electrons stay arranged outside without losing energy and collapsing inward? Some of these questions would be answered by new rules for small systems. Others needed a new piece in the nucleus itself. By the early 1930 seconds, the nucleus looked crowded and puzzling. Protons sit there with positive charge, like charges push apart, yet nuclei hold together unless something disturbs them. Also, measured atomic masses were larger than what you would get by counting only protons and electrons. There was mass without charge that had to be accounted for. People guessed a neutral nuclear particle might exist, but no one had pinned it down in a clear test. James Chadwick focused on a strange radiation that others had already seen when alpha particles struck light elements like beryllium. The beam that came out could knock protons out of other materials. At first it was called gamma rays, a form of very energetic light, but the way it shoved light nuclei suggested something with mass, not just light. Chadwick arranged targets, hydrogen, nitrogen, and others, and measured the speed of the recoiling pieces. Using conservation of energy and momentum, he showed that the incoming agent had nearly the same mass as a proton but no charge. In 1932, he announced the neutron. The neutron solved two linked problems at once. The extra mass in the nucleus came from neutrons, and because neutrons carry no charge, they could sit with protons without adding more electric repulsion. The force that binds the nucleus, the strong nuclear force, acts between protons and neutrons over very short distances and is powerful enough to overcome electric push at that range. The strong force does not show up in daily life because it fades quickly beyond nuclear scales. Inside a nucleus, it does the crucial job. It keeps the core from flying apart. With neutrons in the picture, isotopes made sense. Atoms of the same element share the same number of protons, which sets the atomic number and the chemical identity. But atoms of that element can carry different numbers of neutrons. Those versions have the same chemical behavior because electrons respond to the same positive charge. They differ in mass and sometimes in stability. Carbon 1,2, carbon 1,3, and carbon 1,4 are all carbon. The first two are stable. The last is radioactive and useful for dating old samples. The pattern repeats across the table. Many elements appear in several isotopic forms. The neutron also became a tool. Unlike charged particles, a neutron is not pushed away by electric fields when it approaches a nucleus. Slow neutrons can slip close and be captured, or they can disturb the nucleus enough to cause it to split. That behavior made controlled chain reactions possible. In certain heavy elements, the capture of a neutron can cause fission, releasing energy and more neutrons. Under the right setup, those extra neutrons go on to trigger more fissions. The same idea powers nuclear reactors and also lies behind nuclear weapons. The physics is the same. Control and purpose differ. In stars, the roles of neutrons extend further. Fusion in cores shuffles protons and neutrons into new arrangements, building heavier elements. In extreme cases, matter can be squeezed so hard that electrons are forced into protons, making neutrons. The remnant is a neutron star, where mass is packed so tightly that a small volume holds an enormous weight. These facts come from models and from signals, light particles, and gravitational waves. But the root idea returns to Chadwick's particle, mass without charge that can sit in the core. Chadwick's manner was quiet, but his result was firm. He earned a Nobel Prize in 1935 and continued to work through a difficult period in world history. During wartime projects, he helped coordinate efforts that used neutron physics, the same clarity that led him to test the neutral beam against simple targets, guided his choices in complex settings. The neutron did not shine or spark. It did not make current, yet almost every nuclear process depends on it. With electrons, protons, and neutrons in place, the classic atom had a clearer outline. Electrons arrange outside the nucleus. Protons and neutrons build the nucleus. Forces keep each part in its place over vast ranges of scale. The picture was not the end of the story, but it closed a major gap. Atoms had a structure that matched the numbers. Mass balances made sense. Stability and change could be discussed with specific parts. While the nucleus was being mapped, another question pressed on physics. What is light? And how does it carry energy? For daily life, light is simple. We see by it, warm ourselves with it, and switch it on and off. For theory, light was becoming strange. Experiments showed it acting like a wave in some tests and like a particle in others. People tried to fit both into a single old picture, but the fit would not hold. In the 1800s, the wave view had won most arguments. Maxwell's equations tied electric and magnetic fields together and showed that a changing electric field creates a magnetic field, and vice versa. The math predicted waves that move at a definite speed, the speed of light. The wave model explained reflection, refraction, diffraction, and interference. It matched what lenses and prisms did. It made radio possible. There was comfort in this. Waves were continuous. Energy could be spread out smoothly in space. Then, a small but sharp problem refused to go away: the ultraviolet catastrophe. When physicists calculated how much energy an ideal absorber, a black body, should emit at each color, The classical formulas said that intensity should climb without bound at high frequencies. Warm objects should pour out infinite energy in ultraviolet and beyond. That is not what measurements showed. Real devices made spectra that rose, peaked, and then fell. The peak moved with temperature in a regular way. The formulas had to be wrong somewhere. Max Planck approached the puzzle as a working theorist who trusted data. He sought a curve that fit the measurements and a reasoning that would justify the curve. In 1900, he proposed a sharp assumption. The exchange of energy between matter and light at a given frequency happens in discrete amounts. The size of each packet is proportional to the frequency, with the constant of proportionality, now called Planck's constant. Energy for one packet is E equals hf. With this step, the predicted spectrum matched the observed one across all frequencies. High-frequency radiation did not pile up infinitely because it came in larger packets that were harder to produce at a given temperature. Planck himself did not claim that light is always made of packets. He treated the idea as a rule for emission and absorption. It made the math honest, and it matched the apparatus. Whether the packets were real or just a bookkeeping device, he left open. But the door to a new view was open, and a few years later, someone walked through it. In 1905, Albert Einstein proposed that in some cases, light should be treated as if it consists of discrete quanta traveling through space. He used this idea to explain the photoelectric effect, where light shining on a metal surface can eject electrons. The puzzle was that below a certain color, frequency, no electrons came out, no matter how bright the light was. Above that color, electrons were ejected, even with dim light, and their energies increased with frequency, not with brightness. If light arrives as waves that can build up energy with intensity alone, the cutoff made no sense. Einstein's picture was simple. Each light quantum photon carries energy, E equals hf. To free an electron from the metal, a minimum energy is required in the work function. If the photon's energy is less than that, nothing happens, no matter how many arrive. If the photon's energy exceeds it, an electron can be ejected with the extra energy showing up as its kinetic energy. Brightness then controls how many electrons are ejected per second. More photons, but not the energy of each ejected electron. That energy depends on frequency. Experiments matched these predictions. For this work, Einstein later received the Nobel Prize. The acceptance of photons did not erase the wave side of light. Interference and diffraction still occur and are measured all the time. What changed was the rulebook. Energy transfer is quantized. In some experiments, light acts like a stream of particles, each delivering a packet of energy. In others, it acts like a wave spread in space and time. The right description depends on what is measured and how the system is set up. The move from smooth to quantized was the key. It fixed blackbody radiation and the photoelectric effect and set the stage for more changes. Planck's constant became a core scale for the small world. It sets the size of quantum effects. When actions are large compared with h, classical rules work well. When actions are similar to h, quantum behavior appears and cannot be ignored. This was not a taste choice. It was a fact, forced by data. Devices that count single photons, spectra from hot objects, and currents from metal surfaces under light all demand it. The old dream that nature is smooth all the way down had to give a little. The world is continuous in space and time at the scales we feel, but energy in many small-scale processes comes in steps. Light carries those steps. Matter exchanges them with light according to clear rules. That shift in thinking, from smooth to grainy, where it matters, did not close arguments, it opened them. But things only got weirder from there. Light kept breaking expectations as instruments improved. In the double-slit setup, a lamp or laser shines toward a barrier with two narrow openings. On a screen behind the barrier, bright and dark bands appear. That pattern, alternating stripes, is what overlapping waves make. Water waves do it. Sound waves do it. Light does it too. The surprise comes when the source is dialed down so low that photons pass one at a time. You still get the banded pattern, not a simple two-hole shadow. Single impacts build up, dot by dot, into full interference. The result says each photon has a wave-like spread while it moves and then shows up as a single localized hit when it is detected. That is the core of wave-particle duality. In some measurements, light behaves like a wave. It diffracts, interferes, and spreads. In other measurements, it behaves like a particle. It arrives in discrete packets with energy, E equals hf. What you see depends on what you ask and how you ask it. If you put detectors at the slits to learn which path a photon takes, the interference fades or disappears. You have asked a particle-type question, and the outcome matches that choice. If you do not ask which path, the wave-type pattern appears on the screen. The issue is not human attention or meaning. It is the physical setup that counts. Devices that can, even in principle, reveal the path, change the conditions, and change the result. The same logic extends beyond light. Electrons, neutrons, even large molecules show interference in well-designed experiments. Electrons pass through two slits and form bands on a detector. Neutrons diffract from crystals and map atomic spacings like X-rays do. The rule is steady. Objects we once called particles also have wave properties. Their wavelength is given by the de Broglie relation lambda equals h divided by p, where p is momentum. For everyday objects, the wavelength is tiny, so wave effects wash out. For electrons and atoms, the wavelength can be large enough to see in the lab. Light brings another fixed rule. In a vacuum, it always travels at about 299,792 kilometers per second, about 186,282 miles per second. That speed does not change with the motion of the source or the observer. The constancy led Einstein to special relativity. Space and time adjust so that all observers measure the same light speed. Clocks run at different rates when moving fast. Lengths along the direction of motion contract. Those effects are not add-ons. They are the way the world keeps the speed of light the same for everyone. Quantum and relativity grew side by side. One set of ideas for very small scales, one for very fast motion. While light pushed thinking toward quanta, atoms pushed it towards steps in energy. The spectrum of hydrogen, sharp red, blue-green, and violet lines had been measured with care. No classical orbit picture could pick out those exact wavelengths. Niels Bohr proposed that electrons in a hydrogen atom occupy specific energy levels with allowed orbital radii. An electron can jump from one level to another by absorbing or emitting a photon with energy equal to the difference between levels. Using this rule, Bohr calculated the hydrogen lines and matched the data. The atom, in this view, does not radiate continuously. It radiates when electrons change levels, and only at the allowed energies. Bohr's model was concrete and teachable. It used a small set of postulates tied to Planck's constant to set angular momentum in multiples of He 2 pi. It treated the electron as a particle in a circular orbit and used Coulomb's law for the pull between the nucleus and the electron. It worked well for hydrogen and hydrogen-like ions, where one electron moves around a nucleus. It began to fail for many electron atoms, where electron-electron interactions matter. It also left open a basic issue. According to classical electrodynamics, a charged particle in circular motion should radiate energy and spiral inward. Bohr simply ruled that out for allowed orbits. The rule fits spectra, but did not say why radiation stops in those paths. The next step was to stop forcing electrons to be tiny planets. Erwin Schrödinger wrote an equation that treats the electron as a wave described by a function, C math BF. The square of the wave function's magnitude gives a probability density. Allowed orbits become standing wave solutions called orbitals. They are shapes in space S, P, D, F, linked to quantum numbers that come from the math. Angular momentum is quantized because only certain standing waves fit around the nucleus. The sharp spectral lines arise from transitions between quantized energy levels built into the equation, where Bohr guessed allowed radii, Schrödinger derived allowed energies. Werner Heisenberg arrived at the same physics from a different angle. He built a version of quantum mechanics that manipulates arrays, matrices, of measurable quantities such as transition frequencies and intensities, without drawing pictures of paths. In his approach, position and momentum are operators that do not commute. Hat x hat p hat x equals I h bar. From that algebra comes the uncertainty principle. The product of the spreads in position and momentum is bounded by a small constant, delta x, delta p, j, h bar, 2. This is not about clumsy instruments. It is a limit built into the structure of the theory. You can design an experiment to nail down position more sharply, but then momentum becomes less defined, and vice versa. The uncertainty principle is easiest to see in wave terms. A tightly localized wave packet is made from many wavelengths added together, which spreads its momentum content. A wave with a very precise wavelength has a long, spread-out shape. Localization in space and precision in momentum pull against each other. Time and energy show a similar relation in processes where duration and energy spread trade-off. In everyday life, H-bar is so small that these limits do not matter. At atomic scales, they set the stage for everything. Once you accept probabilities in place of fixed paths, several puzzles clear. Electrons in atoms do not spiral in because they are not little balls on well-defined tracks. They occupy stationary state solutions to the wave equation that do not radiate while they last. Radiation appears when an electron makes a transition between states, and the photon energy matches the difference between the levels. The timing of a single emission event is not predicted. The distribution of many events over time and frequency is. Quantum mechanics also explains interference without invoking a photon, splitting. The wave function spreads through both slits. The probability distribution on the screen includes cross terms that produce bright and dark bands. If a path-revealing device is placed at the slits, the wave function becomes correlated with the device's states, destroying the cross terms and washing out the bands. This is called decoherence in modern language. No special role for a human eye is needed. Any recordable interaction that can, even in principle, distinguish the paths will change the pattern. Another key piece is spin, an intrinsic form of angular momentum that electrons, protons, and many other particles possess. Spin does not mean the particle is a little sphere literally spinning. It is a quantum property that shows up in magnetic behavior and in how particles add to form composite systems. Electrons have spin 1/2, which leads to 2 allowed projections in a magnetic field, up or down. Spin and the Pauli exclusion principle explain why electrons fill orbitals the way they do and why the periodic table has its shape. 2 electrons cannot occupy the same state. That rule builds shells, shell closures, and chemical patterns. Relativity and quantum ideas joined to form quantum field theory for light and matter. For light, quantizing the electromagnetic field gives photons naturally rather than adding them by hand. For electrons and other spin 1-2 particles, the Dirac equation merges quantum mechanics and special relativity and predicts the existence of antiparticles with opposite charge. The positron, the electron's antiparticle, was found soon after the equation was written. These theories keep the central quantum features probability, amplitudes, operators, and h-bar, while respecting the fixed speed of light and energy-momentum relations. On the experimental side, many tests pin down the new rules. The photoelectric effect matched Einstein's photon idea in detail. The kinetic energy of ejected electrons depends linearly on light frequency with slope h and has a threshold set by the material. The Compton effect X-rays scattering off electrons showed a shift in wavelength that treats photons as particles with momentum p equals h, lambda. Electron diffraction measurements delivered clean interference fringes, confirming de Broglie's relation. Precision spectroscopy matched Schrödinger's and Dirac's level calculations, including fine structure corrections from spin and relativity. Back at the nucleus, the strong force that binds protons and neutrons together is now described by quantum chromodynamics, a quantum field theory with quarks and gluons. Protons and neutrons are composite, built from 3 quarks held by gluon fields. Quarks carry a type of charge called color, and the force grows with separation, keeping quarks confined. The strong force is short-ranged at the hadron level because it is carried by gluons and because the effective nuclear force between protons and neutrons is a residual of the deeper interaction. None of this was known in the 1,930 seconds, but the neutron's discovery made room for it by finishing the basic nuclear inventory. As the quantum framework grew, arguments about interpretation continued. Some physicists preferred the Copenhagen style associated with Bohr and Heisenberg. The wave function encodes our knowledge of a system and gives probabilities for outcomes. Measurement yields one outcome according to those probabilities. Before measurement, questions about definite properties are not meaningful. Others, including Einstein, wanted a picture where particles have positions and velocities all along, with the wave function describing incomplete information. Tests of hidden variable ideas later showed that any fully local version of that picture fails for entangled systems. Entanglement is not mystical. It is the statement that the joint wave function of 2 systems cannot be split into independent parts. Measurements on one system then correlate with measurements on the other in ways classical physics cannot mimic. None of these debates change the lab facts that matter for atoms. Spectral lines have precise frequencies that match quantized energy differences. Electron microscopes beat light microscopes because electrons have much shorter wavelengths at useful energies, giving higher resolution. Semiconductors work because electron states in solids form bands with gaps, allowing controlled flow of charge with small pushes. Lasers operate because identical atoms or molecules can be driven to emit identical photons in step when placed in the right conditions. The rules that began with Planck, Einstein, Bohr, Schrödinger, and Heisenberg are built into the devices. A steady theme runs through all of this. What you choose to measure shapes what can be said. A setup that measures position sharply blurs momentum. A setup that preserves path ambiguity lets interference appear. An apparatus that can store which path information removes cross terms and yields particle-like counts. Careful designs can trade one kind of knowledge for another in controlled ways. That is not a flaw in equipment. It is how small systems behave when the scale is set by HE. Even the numbers that look abstract carry weight on the bench. Planck's constant sets the size of every quantum. The speed of light sets conversion between time and space in relativity. The electron's charge, the mass of the proton, and the values of coupling strengths are measured to many digits because engineering and our ability to check theories depends on them. When results do not match to the last place, theory is adjusted or replaced. Quantum theory has survived those checks across many scales because it ties directly to data. The early picture of electrons as dots on tracks gave way to orbitals with shapes and symmetries. The early picture of light as a smooth wave gave way to photons in the right conditions. The old dream of certainty in both position and motion gave way to allowed pairs of spreads that cannot be squeezed past h-bar 2. In return, physics gained tools to calculate rates, spectra, and structures that match what instruments see. The cost was letting go of pictures that cannot be drawn without contradiction. The gain was a framework that let small systems be described honestly. Physicists learned to build experiments that ask one clear question at a time. If the goal is to map energy levels, they measure emitted or absorbed light with high resolution and compare to calculations. If the goal is to see spatial structure, they use scattering and diffraction. If the goal is to follow dynamics, they design pulses and watch how probabilities shift in time. Each choice trades off what can be known sharply against what must stay broad. Measurement at this scale is not a casual glance. It is a planned interaction between system and apparatus with outcomes that depend on the plan. Measurement and system could no longer be kept apart. In the quantum view, what we call a state is a wave function, a rule for computing probabilities of outcomes. An electron is not a marble sitting at a point. Before you measure, it is described by a spread of possibilities, high chance here, lower chance there. A position measurement gives one definite result, but the theory says only the likelihoods were knowable beforehand. After that result, the state you use to make the next prediction changes. The word many physicists use is collapse, but the key idea is simple. The setup and the measurement you choose matter, and they shape what can be learned. A coin under the cup picture is fine as a first step, but quantum superposition is not just hidden information. It is a real overlap of possibilities that can show interference, as in the double slit test. You are not uncovering a pre-written value. You are interacting with a system that will deliver one outcome with chances set by the wave function. Heisenberg's uncertainty principle generalizes that point. Pairs like position and momentum cannot both be squeezed to perfect precision. The product of their uncertainties has a minimum set by Planck's constant. For baseballs and coffee cups, that bound is too tiny to notice. For electrons and photons, it steers everything. This limit did not wreck physics. It redirected it. engineers learned to design devices around quantum rules. Semiconductors rely on allowed and forbidden energy bands. Lasers use stimulated emission from carefully prepared states. Superconductors appear when many electrons act in step to form a new state with zero electrical resistance. The theory is not a license for chaos. It is a framework with firm numbers that match careful tests. The most compact way to use that framework is Schrödinger's equation. It plays the role that Newton's laws play for planets, but for wave functions. Feed in a system's energy landscape the potential, and the equation tells you how the wave function changes in time. The square of the wave function's magnitude gives a probability density. That is why pictures of orbitals around atoms look like dim clouds rather than wires. An s orbital is spherical. A p orbital has two lobes, with a node through the nucleus. Those shapes are not guesses. They are solutions to the equation for the Coulomb attraction between an electron and a nucleus. This shift replaced Bohr's rigid orbits with standing waves. Bohr had been right that energies come in steps, but Schrödinger showed why. Only certain standing wave patterns fit without tearing themselves apart. Each pattern has a specific energy. Jumps between patterns give photons at precise frequencies the spectral lines of hydrogen and its cousins. The math is calm and exact. Boundary conditions, quantized angular momentum, and energy levels that match measured spectra to many digits. As the wave picture took hold, Schrödinger himself pushed on its odd edges. The wave function, taken seriously, describes superpositions not only for atoms, but for any system, large or small. To show how strange that can sound in ordinary language, he drew up the cat in a box thought experiment. A single radioactive atom has some probability to decay in a time window. Hook that event to a detector and a vial, and the setup can be arranged so that a decay would kill the cat. If you treat the whole device by the same rules you apply to atoms, then before you open the box, the combined state includes decayed plus dead and not decayed plus alive parts. Schrödinger meant this to be a red flag. Our everyday world does not look like that. Modern language softens the drama. Large systems interact with their surroundings all the time. Air, light, vibrations. Those interactions spread recordable information into the environment in a process called decoherence. The parts of the wave function that would interfere get separated into branches that no longer mix. What you get is robust outcomes, alive or dead, with probabilities set by the small system's quantum rules. You do not need a human gaze to make that happen. The world is full of measuring devices. In practice, molecules of air, photons, dust, the equation still runs, and the statistics still match. Not every physicist agrees on the words we should use to describe this process. Some prefer to say that outcomes are selected randomly, with Born's rule when a measurement happens. Others say that all outcomes occur in separate branches and that we only ever experience one. What matters for the bench is that the predictions are stable. Spectral lines show where the energy steps are. Tunneling currents in scanning microscopes show that wave functions can leak through barriers. Josephson junctions show phase-coherent quantum motion across insulating gaps. The list of working devices that rely on the same compact rules is long. While electrons were being treated honestly as waves with probabilities, the nucleus demanded its own clarity. Protons crowd together with positive charge. Pure electromagnetism would push them apart. Yet stable nuclei exist. Neutrons were the missing mass and the buffer, but buffer is only a picture. The actual binding comes from a different interaction, the strong nuclear force. It is far stronger than electromagnetism at very short range and drops off quickly beyond distances on the scale of a proton. Inside that range, it holds protons and neutrons together. Explaining such a force with point-like pellets bumping in space was not enough. Physicists shifted to a description in which particles are excitations of fields. This is quantum field theory. Instead of thinking of an electron as a tiny bead flying through empty space, you think of the electron field filling space. An electron is a ripple, a quantized excitation of that field. The same goes for light. The electromagnetic field supports ripples we call photons. The math is organized around fields, creation, and annihilation operators, and symmetries that fix what interactions are allowed. This shift cleans up puzzles that the old pictures left behind. In quantum field theory, conservation of energy and momentum, plus the symmetries of the fields, determine which processes can happen and with what probability. Forces are described by the exchange of field quanta. The electromagnetic force appears when charged particles exchange photons. The weak force appears when particles exchange W and Z bosons and is responsible for processes like beta decay. The strong force appears when quarks exchange gluons inside hadrons and, at larger scales, as a residual force between protons and neutrons. The strong interaction, in particular, is special. The theory that describes it, quantum chromodynamics, assigns a color charge to quarks and uses gluons to carry the force. Unlike photons, gluons carry the charge they mediate, so they interact with one another. The result is confinement. Try to pull quarks apart, and the field between them tightens like a cord. Energy poured into the system makes new quark-antiquark pairs rather than freeing the originals. That is why protons and neutrons behave as single units in low-energy experiments, and why the nuclear force between them is short-ranged and complex, a leftover from deeper color forces. What began as a language for electrons in atoms scaled up, fields allowed a single framework for particles to be created and destroyed, for interactions to be computed systematically, and for infinities to be handled by renormalization so that final predictions are finite and testable. This is how precise numbers like the electron's magnetic moment are calculated and then checked to astonishing accuracy. The same approach explains why radioactive decays have specific lifetimes and energy spectra. It links atomic physics, nuclear physics, and particle physics under one method. The observer's role is still present, but it is now framed in terms of interactions between systems. A measurement is an interaction that correlates the state of a small system with states of a larger one. A detector, a screen, a crystal. The wave function of the combined setup evolves according to the same equation as long as the interaction lasts. Afterward, records exist in the macroscopic system that we can read. Probabilities from amplitudes become frequencies in those records. You can draw the boundary between system and apparatus in different places. The predictions do not change. Even with this clarity, everyday language can trip us. Particle suggests a tiny solid thing. Wave suggests a moving wiggle in a medium. In quantum field theory, the objects we detect are quanta, discrete packets of excitation in fields. They are localized when and where a detector clicks. But the rules that set the chance of a click come from amplitudes that can spread and interfere. When a beam of electrons forms an interference pattern, it is those amplitudes that combine. When a Geiger counter ticks, it is a quantum of the field depositing energy in the gas and triggering an avalanche. The picture is consistent across phenomena, as different as semiconductor devices and cosmic ray showers. At very short distances and high energies, fields reveal more structure. Unification attempts show that electromagnetic and weak forces join at a scale into the electro-weak force, described by a single framework, with symmetry broken at low energies, so that photons stay massless, while W and Z bosons are heavy. The mechanism that breaks the symmetry appears as a field that permeates space, the Higgs field. Quanta of that field are Higgs bosons. Particles that interact with the Higgs field acquire inertial mass in the equations. This is not an extra push. It is a parameter in the relation between momentum and velocity that appears because the field has a non-zero value everywhere. These are compact statements, but they grow directly from the same practices that guided earlier steps. Write the simplest rules, consistent with symmetries and tests. Compute what the rules predict, and compare with data that are cleaned of bias and noise. The program is not complete. Gravity is not yet joined to the rest in a quantum field theory that works at all scales. But within its range, the field picture has explained why atoms are stable, why nuclei exist, why light and matter trade energy in steps, and why devices from LEDs to MRI scanners do what they do. Returning to the strong force, the field view also explains why nuclear binding has a range. Exchange of massive field quanta produces forces that fall off quickly with distance. The effective carriers between protons and neutrons in nuclei can be modeled by pions and other mesons, which stand in for complex gluon-quark dynamics at low energies. That model gives the right rough sizes and binding energies of nuclei, and why some arrangements are magic numbers shell closures in the nuclear sense. Numbers that once looked like catalogs become outputs of the same kind of standing wave logic that fixed atomic shells, but now inside the nucleus. None of this requires thought-stopping metaphors. It requires patience with a small set of core ideas, quantization set by fixed light speed, states as vectors in a space where probabilities come from squared amplitudes, fields as the objects that exist everywhere, with particles as their quanta, and interactions as the ways fields couple, fixed by symmetry. From those points, detailed behavior follows. The equations look abstract, but they are anchored to detectors, spectrometers, beams, crystals, and circuits that return the same numbers wherever they are used. That is how the observer returns to the lab bench as a builder. We choose which amplitudes are allowed to meet, which paths can interfere, which records we keep, and which we erase. We choose energy scales and time windows. The mathematics then gives probabilities. Apparatus turn those probabilities into histograms. If the bars do not match, the model changes. If they do, confidence grows and the result gets added to the short list of rules that other fields borrow. In a field picture, interactions are exchanges. A field can produce a quantum and later absorb it. Two electrons that repel do not push directly. One emits a virtual photon and the other absorbs it. The bookkeeping keeps energy and momentum conserved across the whole process. The photon is virtual because it does not have to obey the free particle relation between energy and momentum during the brief exchange. The same logic carries to the strong interaction. There, the messengers are gluons, and their couplings are stronger at the short distances inside hadrons. Gluons also carry the charge they mediate, so gluons interact with one another. That feedback is why the force grows as quarks are pulled apart, and why individual quarks are not seen as free particles. Protons and neutrons are composites. A proton contains 2 up quarks and 1 down quark. A neutron has 1 up quark and 2 down quarks. Around those valence quarks, the gluon field seethes and can briefly form quark-antiquark pairs. The effective picture is a bound state with a busy interior, not 3 marbles stuck together. The quantum number that organizes strong interactions is called color. It is not visual color. It is a label for how quarks and gluons transform under the symmetry of the strong force. Color must balance to a neutral whole, which is why only colorless combinations, 3 quarks, a quark with an antiquark, or multi-quark, states that net to neutral are observed as isolated particles. As accelerators improved, many new particles appeared in detectors. Muons look like heavy electrons. Pions and kaons are mesons, made of quark-antiquark pairs. Short-lived states fill out families with similar spins and parities. For a time, the particle zoo looked like an unsorted cabinet. Order returned when quarks, leptons, and force carriers were arranged under a single scheme, the Standard Model. Matter comes in 2 basic families: quarks up, down, charm, strange, top, bottom, make hadrons by binding through gluons. Leptons, electron, muon, tau, and their 3 neutrinos do not feel the strong force. Forces are carried by gauge bosons, photons for electromagnetism, gluons for the strong force, and the W and Z for the weak force. The Higgs field gives W and Z their masses and sets the inertial masses of quarks and charged leptons through their couplings. This framework is practical as well as tidy. It predicts processes and rates that match measurements across many orders of magnitude. It explains why beta decay changes a neutron into a proton plus an electron and an antineutrino through the weak interaction. It accounts for the patterns in electron shells and chemical bonding as consequences of the electron's quantum numbers and the Pauli exclusion rule. It gives cross-sections for scattering at colliders that experimentalists can test against histograms. The 2012 discovery of the Higgs boson in proton-proton collisions fit the last major missing piece of the model's mechanism. The Standard Model is not a final map. Gravity is not included in a quantum form that works at all scales. The model does not explain the values of its many input numbers. It leaves dark matter and dark energy outside its borders. Neutrinos, once thought massless, oscillate between flavors, which means they have tiny masses that require extensions. Those open issues do not weaken what the model does cover. They define where new data must speak. Nuclear physics sits one level up, where the strong force's residual effects bind protons and neutrons in nuclei. Here, the language shifts from quarks and gluons to nucleons and mesons as effective carriers. The nuclear force is short-ranged and saturating. Each nucleon binds mainly with its neighbors, which leads to roughly constant nuclear density across elements. Shell effects appear again, now in the nucleus. Certain numbers of protons or neutrons give extra stability magic numbers because standing wave patterns fit the nuclear potential well. Heavy nuclei can be made to split. In fission, a large nucleus such as uranium-235 absorbs a neutron and forms a compound nucleus that deforms and passes over a barrier. It breaks into 2 medium mass fragments plus 2 or 3 free neutrons and releases energy. The energy appears as kinetic energy of the fragments and as gamma rays. The mass of the final products is slightly less than the initial mass. The missing mass has become energy according to E equals mc, 2. The extra neutrons make a chain reaction possible if, on average, one of them causes another fission before escaping or being absorbed. The first clear evidence came in 1938, 1939, when Otto Hahn and Fritz Strassmann found barium among the products of neutron-irradiated uranium. Lise Meitner and Otto Frisch interpreted the result as nuclear splitting and estimated the energy release with a liquid drop model. The numbers were large enough to matter far beyond the lab. A self-sustaining chain reaction required only the right geometry, a moderator to slow neutrons, and materials that absorb or reflect neutrons in planned ways. A chain reaction that grows faster than neutrons are removed gives a burst. That logic became the basis of weapons during World War II. Uranium-235 and plutonium-239 were used because they fission readily with slow neutrons and can support rapid multiplication when assembled into supercritical shapes. Devices were built, tested, and used. The physics is straightforward. The consequences are severe. The same neutrons that maintain a chain reaction also activate materials and produce fallout. The scale of release is set by mass converted at C2, which is large for even small mass changes. The same process can be held to steady power. In a reactor, fuel rods contain fissionable material. A moderator, often water or graphite, slows neutrons so that they are more likely to cause fission in the fuel. Control rods made of materials that absorb neutrons, such as boron or cadmium, are inserted or withdrawn to keep the average number of fissions per generation near 1. Coolant removes heat to make steam for turbines. Shielding and containment limit radiation and trap fission products. Fuel cycles differ by design. Some reactors breed plutonium or use thorium paths. Others are optimized for power with minimal breeding. Fission's advantages are clear: very high energy density and no carbon dioxide from the chain reaction itself. Its challenges are equally clear: long-lived radioactive waste that requires secure storage, accidents that can release radionuclides if safety systems fail, and proliferation risks when fuel cycles can be diverted. Designs aim to reduce those risks with passive safety features, fuels that run cooler, and systems that shut down by physics if power or cooling are lost. The engineering is as central as the nuclear equations. Fusion runs in the other direction. Light nuclei join to form heavier ones and release energy because the binding energy per nucleon rises up to iron. In stars, gravity provides confinement and pressure. On Earth, two main paths are pursued. Magnetic confinement traps a hot plasma in a torus, tokamaks, and stellarators long enough that collisions between deuterium and tritium can fuse and release energetic neutrons and alpha particles. Inertial confinement uses short, powerful laser pulses to compress and heat tiny fuel pellets so rapidly that fusion reactions occur before the pellet can fly apart. Both approaches must beat losses. The Lawson criterion states the needed product of density, temperature, and confinement time. Deuterium-tritium is favored because it has the highest fusion cross-section at low temperatures by fusion standards. Materials and fuel handling become central immediately. Fast neutrons from DT fusion damage structures and make them radioactive. Walls must withstand heat and particle loads while maintaining shape and strength. Tritium does not occur naturally in large amounts and must be bred from lithium inside the reactor using the same neutrons that fusion produces. Superconducting magnets provide fields strong enough to hold plasmas, and those magnets have to be cooled and protected from radiation. Diagnostics measure profiles and instabilities so that control systems can keep a plasma from wrinkling or erupting. Short pulses of net energy gain have been achieved in certain experiments, and magnetic machines have held plasmas stable for long durations at high temperatures. None of that yet constitutes a grid-scale power plant. Work continues on heating methods, turbulence, suppression, stellarator optimization, and wall materials that handle heat loads. The physics of fusion is firm. The challenge is integration at scale with reliability and cost. Nuclear science reaches beyond power. Medicine uses radioisotopes for imaging and for therapy. Positron emission tomography depends on tracers that emit positrons. When positrons meet electrons, they annihilate into 2 gamma rays that detectors can triangulate. Targeted radiotherapy uses beta or gamma emitters, placed or directed near tumors, to damage cancer cells more than surrounding tissue. In diagnostics, technetium-99 meters remains common because its gamma energy is well suited to imaging and its half-life limits dose. Nuclear magnetic resonance, a quantum effect in nuclei, underlies MRI scanners. The nuclear was dropped from the name for public comfort, but the physics is nuclear spin in a magnetic field. Earth sciences use radiometric dating. Carbon-14 dating measures the time since living tissue last exchanged carbon with the atmosphere. Uranium, lead, and potassium-argon clocks extend to geologic ages. In materials science, neutron scattering reveals atomic positions and motions in crystals because neutrons interact strongly with nuclei and are sensitive to light elements that X-rays can miss. In industry, sealed sources inspect welds, sterilize equipment, and gauge thickness on production lines. In space, radioisotope thermoelectric generators power probes where sunlight is weak or intermittent. Back inside the nucleus, the weak force explains certain decays that change one element into another. Beta decay turns a neutron into a proton while emitting an electron and an antineutrino, or turns a proton into a neutron with a positron and a neutrino. The spectra of emitted electrons are continuous because the energy is shared with the neutrino, a particle detected directly, only later with very low interaction probability. Neutrinos pass through matter with little effect. Detectors use huge volumes of water or heavy liquids and look for rare flashes when a neutrino nudges an electron or a nucleus. At higher energies, field theory unifies electromagnetism and the weak force. Above a particular scale, the differences between them vanish in the math. At lower energies, the symmetry is hidden by the Higgs field, taking on a non-zero value everywhere. The result is a massless photon and massive W and Z bosons. Experiments measured the W and Z masses and their decays as predicted. Precision tests constrain small deviations and guide where new physics might appear. The same framework explains why some processes are rare in nature. Symmetries and conservation rules prevent them or suppress them to levels below current reach. Across these topics, one design principle keeps appearing. Use the simplest model that respects measured symmetries and conservation laws. Compute probabilities for events. Build apparatus that can see the relevant signals above background. If results disagree, refine the model or the inputs. If they agree, push to new regimes where disagreements might show. That cycle is why the same core numbers, like cross-sections, lifetimes, and energy levels, show up in tables that engineers and doctors actually use. Even at rest, ordinary matter is active at small scales. In a chunk of metal, electrons fill bands up to a Fermi energy and move when pushed by a small field. In a crystal, phonons quantized vibrations of the lattice carry heat. In a nucleus, Protons and neutrons shift positions under a potential that balances attraction at short range against Coulomb repulsion at longer range. Virtual excitations of fields appear in loop calculations and correct measured values by tiny amounts that can be resolved in precision experiments. The picture is not noise. It is structure that averages to stable behavior at larger scales. Fission, viewed schematically, has a few moving parts that matter for control. A thermal reactor uses a moderator to slow neutrons to energies where the probability of fission in the fuel is high. Some neutrons are promptly emitted in each fission. A tiny fraction are delayed, coming from the decay of fission fragments seconds later. Those delayed neutrons make fine control possible. They give time for rods and feedbacks to act. Criticality, steady power, means exactly one neutron from each fission, on average, causes another fission. Subcritical means fewer than one. Supercritical means more. Control rods and soluble absorbers hold that average near 1. Coolant removes heat, and temperature feedbacks in fuel and moderator add passive stability by reducing reactivity as things warm. In reactor cores, in medical tracers, in fusion trials that try to bottle a small star, the atom's energy is at work. The question is no longer whether we can touch that fire, but how we guide it. A few centuries ago, atoms lived mostly in margins and lectures, ideas drawn in chalk and argued by lamplight. Today they are components we arrange, signals we read, and tools we build into circuits, scanners, and standards. The invisible became practical. The abstract became adjustable. Look around any room, and you'll spot devices that only exist because we learned to treat atoms as quantum systems with energy levels and shared bands. Modern electronics stand on semiconductors, especially silicon. Pure silicon conducts poorly. Add a trace of phosphorus, and it contributes loose electrons. Add a trace of boron, and it creates electron vacancies called holes, p-type. Join P and N regions and you get a junction that passes current one way better than the other. Layer millions and then billions of these junctions into transistors and logic gates, and you get microprocessors. The jump between off and on is a matter of electrons crossing a barrier, a quantum story told in nanometers. Doping is not a guess. It is counted atoms per cubic centimeter, placed so that energy bands bend just enough to switch with tiny voltages. Each chip is a city of gates, clocked in rhythm, built from atomic scale neighborhoods that push and pause electron flow in reliable steps. Hospitals rely on the same scale, only pointed at the body. Magnetic resonance imaging aligns the tiny magnetic moments of hydrogen nuclei in water and fat. A radio pulse tips those moments. As they relax, they emit radio signals whose timing and phase depend on local chemistry and structure. Gradient coils vary the magnetic field across the body, encoding position into frequency. Software reconstructs the signals into slices and volumes. There is no ionizing radiation in this method. The nuclear, in the original name, refers to nuclei and their spins. The images are detailed because the physics is specific. Hydrogen is abundant, its magnetic resonance is strong, and its surroundings change relaxation times in measurable ways. Nuclear medicine uses unstable isotopes as tracers and treatments. A positron-emitting tracer reveals metabolism in real time as the positrons annihilate with electrons and produce paired gamma rays detected in rings around the patient. Iodine 131 can calm an overactive thyroid because the gland naturally concentrates iodine. The radiation then acts where it is needed. Other therapies load molecules with isotopes chosen for the right range and energy. so that tumors receive the largest dose while nearby tissue receives less. None of this is guesswork. Half-lives, energies, and tissue pathways are tabulated and matched to clinical goals. Working even smaller, nanotechnology reshapes materials by arranging atoms and patterns at the billionth of a meter scale. Properties shift because surfaces dominate, and quantum confinement alters electron behavior. Gold nanoparticles absorb and scatter light differently from bulk gold, turning solutions red or purple. Carbon arranged as graphene, a single atomic sheet, conducts and bends in ways a thick lump of carbon never could. Carbon nanotubes can be both strong and flexible. Surfaces with nanoscale textures repel water and stains because droplets rest on tips and roll off. Drug carriers made from nanoparticles can be tuned to attach to certain receptors, release over time, or respond to pH. Tools like the scanning tunneling microscope move a sharp tip across a surface and measure electron tunneling to map atoms directly. With care, that same tip can nudge atoms into designed shapes. This is fabrication by counting. Quantum computing pushes the same physics into a new role. A classical bit is 0 or 1. A quantum bit, or qubit, uses superposition so that its state is a weighted combination of 0 and 1 until measured. Entangled qubits share correlations that no classical system can mimic. Algorithms that exploit interference among many paths can factor large numbers, search spaces, or simulate quantum systems much faster than ordinary code for certain tasks. The hardware varies. Trapped ions held in electromagnetic fields and addressed by lasers, superconducting loops whose quantized currents mark distinct states, defects in diamond that serve as solid-state spins, photons routed through interferometers. In each case, noise and loss of coherence are the challenge. Shielding, error correction, and clever control circuits work to keep quantum states intact long enough to compute. Even in this early era, the machines demonstrate that quantum rules can be engineered, not only observed. Atomic timekeeping makes navigation and communication precise. Cesium and rubidium clocks count a specific frequency associated with a transition between hyperfine levels in the atom's ground state. Laser-cooled atoms reduce motion that would blur the tick. Optical clocks push accuracy further by counting much higher frequencies in optical transitions. Dividing down yields an extraordinarily stable second. Global navigation satellites broadcast time codes from such clocks. Receivers compare arrival times from several satellites to solve for position. The same discipline synchronizes communication networks, coordinates financial trades, and calibrates physics experiments. An atomic second is not a metaphor. It is a repeated quantum event, counted so consistently that drift is tiny over years. Everyday industries use atomic tools in quiet ways. Ionizing radiation sterilizes medical instruments and food without raising temperatures. Neutron beams probe crystal structures and magnetic order that X-rays miss. Ion implantation tunes semiconductor layers. Electron beam lithography draws patterns below the limits of optical light. Radiocarbon dating measures the tiny remaining fraction of carbon-14 inches organic remains to tell a timeline for artifacts and bones. Other isotope systems, uranium-lead, argon-argon, extend the reach into deep Earth time. In space, radioisotope generators power probes where sunlight is scarce, compact cores, warm electronics on the night side of distant worlds. The nuclear story that began with fission remains a study in control. In a power reactor, Geometry and materials make the average number of new fissions per fission equal to 1. Moderators slow neutrons. Control rods absorb extras. Coolant removes heat. Delayed neutrons emitted seconds after fission by certain fragments provide a buffer that lets operators move the core smoothly. Shielding and containment trap radiation and products. Waste forms are isolated and counted in decades to millennia, which means storage designs must survive politics and weather, not just heat and pressure. The physics is clean, the responsibility is long. Fusion tries a different approach. Heat light nuclei until they combine, releasing energy because the binding energy per nucleon increases. Lab plasmas need temperatures above 100 million degrees and careful confinement. Tokamaks and stellarators use magnetic fields to guide charged particles on nested paths. Laser-driven capsules use pulses to compress fuel faster than it can escape. Energetic alpha particles from fusion help heat the plasma. High-energy neutrons carry energy to walls, where it can be collected. Tritium must be bred from lithium. Walls must resist neutron damage. Heat exhaust must be managed. These are engineering problems with firm physics under them, and each year brings better confinement, longer pulses, and smarter materials. Not all atomic work is grand. Some of it is local and steady. A smoke detector counts alpha particles and notices when smoke blocks them. A materials lab uses ion beams to check the thickness of a coating. A pipeline is scanned for weld defects with gamma radiography. A cancer clinic listens for the gamma rays from a tracer to see how a therapy spreads. The methods are simple. In outline, count quanta, measure energies, compare to tables, and powerful in practice. Step back and the pattern is consistent. The atom is not a pebble, but a set of allowed states coupled by forces. Electrons fill orbitals with rules set by spin and symmetry. Nuclei bind through a short-range strong force that overwhelms electric repulsion at femtometer scales. Fields extend through space. Their quanta appear as particles when they interact with detectors. Measurement is an interaction that leaves records in macroscopic systems. Every reliable technology named here is a narrowed version of that story, with a clear question asked and a clear signal taken from the answer. From the first arguments about indivisible pieces to the present day of patterned wafers, tuned isotopes, and laser-cooled clocks, the theme has held. Small systems follow rules that are stable enough to be built upon. We do not need to see an electron to shape its band structure. We do not need to peek inside a nucleus to plan a therapy dose. We match models to outcomes, tighten the match with better instruments, and fold the result into tools other people can trust without revisiting the derivation. That trust carries obligations. In power, it means designs that fail safely, records that last, and openness about limits. In medicine, it means doses that are justified and detectors that are calibrated. In computing, it means honesty about what quantum machines can and cannot yet do. In research, it means measurements that can be repeated and uncertainties that are stated plainly. The atom grants reach. It also requires care. We do not stand at an endpoint. Open problems remain. How to join gravity to quantum rules? What dark matter is made of? Why the constants of nature take the values they do? How to make fusion in practice as steady as it is on paper? How to build qubits that scale without losing coherence? None of these questions erase what we already use daily. They simply point beyond the lamplight to regions where more tables and more tools will come. For now, it is enough to notice how much of the modern world rests on the quiet behavior of small things. Electrons slip through gates and paint images and speech on glass. Hydrogen spins tip and ring, making pictures inside the body. Tracers flash and fade, carrying news from tissues that cannot speak. Clocks count transitions, while satellites arc above. Nanostructures bend light and water. In each case, the plan is the same. Prepare a state, let it evolve, detect the outcome, compare to the rulebook, and use the difference to guide the next step. What began as a whisper in philosophy has become a working language in laboratories and factories. The atom is not an answer. It is a platform. We shape it, listen to it, and learn from it. And as we do, the world made from its patterns becomes more legible, more adjustable, and, with care, more humane. As night settles, let that thought linger. The smallest, least certain parts of nature give rise to the most stable structures we know: materials, signals, memories. The same rules that limit what can be known allow what can be built. Breathe in, breathe out, and let the steady pulse of those rules carry the mind to quiet. The hum of electrons in the wall, the soft tick of distant clocks, the faint wash of cosmic light through the atmosphere, all of it is the same story at different scales. Let it fade to a low murmur and rest.